Hi, I'm Dave Erickson, and this is my DIY-SMU project. DIY-SMU is a 4-quadrant source measure unit. It has 6 current ranges and 3 voltage ranges. The 3 voltage ranges are from plus or minus 1.5 volts up to plus or minus 150 volts, and the current ranges are from 1 microamp full scale to 100 milliamps full scale. I'd like to give you a little demo, a tour of the inside, and then I'll describe what's next in the project. The project is not 100% complete. The core functions are working, but I still need to fix up some of the software and some of the hardware as well. But at least the main functions and all the ranging are all working. So this is the front panel. Front panel is a touchscreen display. And you can see what's being displayed is the force voltage VF and IM, current measured. So right now I'm forcing 50 volts, but only measuring 1 milliamp because it's clamping. So let me disconnect the load. The jacks on the right are these are the force output jacks. These are the remote sense jacks. This is the guard, and this is the ground, the chassis ground. You can see I didn't have a green jack. There's front panel controls. There's one to control the value, and there's a couple of buttons down here to control the digit selection. So right now we're at 50 volts, and I can move you can see I can move the cursor. These control the cursor, so I can move the cursor around 50, 60, 70, 80, 90, 100 volts, and I can go up from minus 150 to plus 150 volts. And let me plug in my voltmeter. And you notice that there's a current reading now, and that current reading is the when it first happened, I thought, oh, there's an error I'm going to have to fix, until I realized that current reading is because of the 10 megohm input resistance of the benchtop meter causing a current to flow at different voltages. So at 70 volts, you can see I'm drawing, at 100 volts I'm drawing 9.9 microamps. And at minus 100 volts, it's roughly 10 microamps. It's like, ooh, I wasn't used to using I wasn't used to measuring very tiny currents. And so when I first built this thing, and it displayed current readings, I thought, oh, this is a problem. Then I realized, no, it's working. It's measuring a very small currents. So, give you a quick tour. The front panel. This button sets the voltage range. There's 3 voltage ranges: plus or minus 15, plus or minus 1.5, and plus or minus 100 volts. 150 volts, sorry. Current ranges, you can see there's a little bug there. 1 microamp up to 100 milliamps. So let's set it for the 1 milliamp range for now. These 2 buttons control the cursor position, left and right. These 2 control the value, up and down. This button controls whether it's, right now it says FVMI, which is force voltage measure current. So I'm forcing a voltage and measuring a current. when you hit the button. Then it goes to force current and measure voltage. And it goes to the full, it's on the 15 volt range, so it goes to full voltage, whatever the voltage clamp is set to, which is currently 15 volts. And there's an on-off button, which is currently not implemented, so the output is always on. And then the next button controls the, goes to the next page of the display. And the next page is the clamp setting, where we set the clamp plus, clamp minus, clamp current plus and minus, and clamp voltage plus and minus. And you can see there's some voltage settings and current settings there. And again, we use the left and right buttons and the up and down buttons. The right button controls the cursor, and since you don't use this as often, I needed a way to select which parameter you're changing, so I just use the next button to go to the next cursor position. And then the third screen, which is not implemented yet, is the plotting. My plan is to implement plotting on this, but I haven't done it yet. And then it loops back, goes to the main screen. So let's set it for 0 volts. Go to the 150 volt range. So you can see. And then let's look at the readings on the meter, get a rough idea what kind of accuracy we have here. So I'm using a HP 34401 meter. So that's 60 volts, 90 volts, 20 volts, 10, 0. 0 offset is pretty good. It's reading around a millivolt. Minus 10, minus 20, minus 70, and all the way up to minus 150 volts. And then on the 15 volt range, you get 10 times the resolution and a little bit lower noise. And you can see there's 5 volts, 4.99. Lots of 9s, not quite enough. The calibration is not perfect. I haven't calibrated this thing in quite a while. Minus 5. And offset error of about 0.06 millivolts, so 60 microvolts. So that's pretty good. So let's go on to the force current. So force current, you notice, first thing you notice is that the voltage goes in force current. Notice that the voltage goes to the maximum voltage, which on the 15 volt range is this. And if I go positive current, it goes positive, and if I go negative current, it goes negative 15 volts. And the reason is because there's no load, so it's acting as an ideal current source. Of course, if you put it in the 150 volt range, it goes all the way to a plus or minus 155 volts, just by changing the current a little tiny bit. So yeah, so obviously you have to be careful with setting the clamp values. For the clamp is what limits the voltage in current mode, and of course putting a load on. So now I'll put a 1K load on, so at 1 milliamp, and see, it induces 1 volt. Let's go to the lower voltage range. There's the voltages as a function of the setting. I noticed that there's an error on the force voltage. Okay. Let's try higher current range. So this is the 10 milliamp range. Yeah, this one's, I think the 1 milliamp range must not be calibrated. Yeah, I got a pretty significant error on the 1 milliamp range. 10 milliamp range, and here's the 100. Oops. Let's go back to 15, and then current, high current. So this is the high current range, so it's 46 milliamps. Oops. And let's put a heavy load on there. So this is about a 70 ohm resistor. You can see there's the current as the voltage as a function of the current. There's about 140 ohm load. Let's go to the high voltage range. And we can go up to 105 milliamps is the maximum. Okay, I'd like to give you a tour of the inside. We can get the cover off. So there are two main circuit boards inside. That's the board on the left is the main board, and the board on the right, which is buried down inside there, is the amplifier board. So the amplifier board, you can see, mounts to a heatsink, and that board has the high voltage power supply, the plus minus 170 volt power supply, and all the output transistors. You can see there's a small cooling fan in the back. Underneath the main board, let's see if you can see this. Let's see, there's a toroid transformer, that's the large white item. There's a line filter in the back, and a 12 volt power supply, which you can't really see, in the front. So the entire instrument is powered from the toroid transformer that provides the high voltage, and the 12 volts, which provides the low voltage. If you look behind the LCD, you'll see the CPU. The CPU is just a fairly generic. I built it myself, but it's my own design. But it's a Arduino, Leonardo type Arduino board. And I'm basically just using it for the single chip and a couple of connectors. So that ribbon cable that's coming off it and going to the back, that's the SPI controls and the power for the main board. You can see I have a couple of wires dangling here. The 12 volts is not hooked up internally yet, so I'm just using the lab supply to provide 12 volts. And the USB cable is also just dangling in the back. That's this black cable coming up the side here. And the wiring is a little messy. So one thing about this enclosure is it's a tight squeeze. The power board is a little too long for the enclosure. The main board fits okay, but it's too tight for a do-it-yourself kind of project. So I'm looking for a half rack 2U size enclosure off the shelf, but I cannot find anything. I've searched the world high and low. Nobody builds an off-the-shelf enclosure for that kind of project. This is a front panel controls, just the knob, the encoder knob, and the 4 buttons. There's a little ribbon cable that comes off there and goes to, it's literally soldered directly to the CPU board. And I use the next-gen display, which only uses a 4-wire interface for the LCD, and that works out pretty well. And that's these 4 wires right here. So let's see. Yeah, let me give you a quick tour of the main board. Let's see if I can zoom in a little bit. So in the back we have this is the plus or minus 15 volt power supply. So this connector takes in 12 volts and 5 volts. So the 5 volts is only for the isolation circuit. So the non-isolated side of the 5 volts, that's the same 5 volts that runs the Arduino. There's the isolators. The DC to DC, which is this guy, a little 3-watt plus or minus 15 volt DC to DC, is also isolated. So it's an isolation barrier that runs through there. So the whole instrument is isolated except for the all the analog circuitry for the instrument is fully isolated. A little bit of filtering. Next to the interface is the A to D, which is a 24-bit sigma delta part, and a D to A, which is a 16-bit 4-channel D to A. And these are some signal conditioning op amps that provide that take the A to D and the D to A and use it to convert it to plus or minus 5 volt signals. The instrument runs off plus or minus 5 volts. This next section here is the crossover. That's what does the automatic switching between current and voltage control. And it provides the clamps, the current and voltage clamps. These 2 ICs are control registers that provide 16 bits of control. They set the current and the voltage ranges. The remote sense, they turn on remote sense, and they turn on and off the output, and they set the mode of the instrument. So next in line, this is the current ranging. These are the high current 100 milliamp. Notice there's another solid state relay and extra resistors for an optional 1 amp range someday. But for now, we use 100 milliamps as the maximum range. And then this is the 1 microamp range resistor, and then the 1 microamp, 10 microamp, all the different low current ranges. These green connectors are for the output and remote sense connections. Also, these 3 wires interface to the amplifier board. These op amps here are the voltage sense, remote sense amplifiers. This solid state relay, the white guy, is for the voltage ranging. That switches to the 100 volt, 150 volt, or the 15 volt range, and down here are the difference amps for the current and voltage. So yeah, that's the main board. The amplifier board, that's the board that takes in a plus or minus 10 volt signal and outputs up to plus or minus 150 volts. That's the main amplifier board, and the power supply for that is on the same board. So what's next on the project? Next is to finish up the user interface and fix a few bugs. clamp screen needs some work. Right now, the CPU board is just sort of thrown in. So to build a proper CPU board, including a front panel, so that'll have the front. Hopefully, the front panel controls the CPU will mount right behind it. So the Arduino does a pretty good job. I'm not even close to running out of RAM or program memory, and it's plenty fast enough. It has a USB interface. I have plenty of I/O. So even though Arduino is doing a basic Leonardo 8-bit Arduino is doing a really nice job on the user interface, I do need more memory if I want to start plotting. So one of the key features that I'd like to add is the ability to plot the output data, the measure values over time. In order to do that, I'm going to need more than a couple of K of memory, and for that I'm thinking of using a Teensy processor. I've used them in the past. They're great. It's a little $20 module, and it has I think 64K of memory. So about, what is that, 4K versus 64K, so 16 times the amount of memory of a basic Arduino. And some of the libraries that they have are very nice. So that's in the future. Obviously, I have to add the remote sense and the output on relays. Those are not on the board right now. Just getting the basic functionality working without those was challenging enough. I need to come up with an improved package. So this current configuration will almost fit if I reduce the amplifier board length. And when I made it, I put plenty of room on the board. So reducing the size, it's not a very dense board, so reducing it is pretty straightforward. So that will allow me to package in this one container, but there's still other issues. I want a front panel power AC switch, and there really isn't room for it on this front panel. There's an extrusion that runs along the length of the chassis, and that extrusion is almost touching the edge of the Nextion display. Here's another Nextion display, and you can see there's a lot of the display sticks out on the right side, so you can't really use that side of it. I possibly could put a little tiny toggle switch here for AC, but it's a tight squeeze. The other thing is, and this is a safety issue. Right now I'm using 5-way banana jacks just because they're convenient, but for safety, an instrument like this should use safety recessed banana jacks, and actually they're larger. They take a larger diameter, and even just the larger diameter barely fits on this. And then another safety issue is that the buttons are way too close to the jacks here. I really need another almost a half an inch of height to be able to separate the encoder knob and the buttons from the high voltage. You shouldn't be reaching close to the high voltage to hit the controls. So, as I said before, I couldn't find a half rack. Half rack means, rack mount is 19-inch minus about an inch on each end for the ears. So the enclosure for a rack, full rack wide enclosure is about 17 inches. So half of that is about 8.5 inches. So a half rack box, and you can see that all these HP instruments are half rack. The power supplies are half rack. So there's a lot of half rack equipment out there. So it would be nice to make this half rack. That way it would stack nicely on top of existing test equipment. But anyway, as I said, finding an off-the-shelf half-rack box was not available. So I'm looking at various ways that I can build a half-rack box, and that will make this enclosure almost an inch wider, almost a half an inch taller, and an inch or two longer, which, you know, I'm not crazy about making the product bigger, but you know, if that's the way it is, that's the way it is. Another thing that has not been added, an instrument like this requires a remote control. And there are a lot of different ways of doing remote control over USB or Ethernet or GPIB or whatever. USB certainly is almost free with this processor. So my plan is to, you know, I'm not an expert on protocols, and there's standards out there for instruments. There's LXI, and there's also Skippy. You can do low-level GPIB, you can do low-level serial. There's a lot of ways to control an instrument, but I think the best way to do it is with Skippy. Source instruments like this, source measure instruments like this, have plenty of existing Skippy commands, so I don't have to go invent a new command structure for it. I can just use the existing commands. And I wouldn't be talking this way had I not discovered recently that a Skippy library for Arduino exists. And I haven't tried it, I haven't downloaded it, I haven't run any examples. So yeah, I figure I'll try to get that working, and that would be a good way to control the instrument remotely. Another thing that's needed on this project is to automate the calibration. Right now there's gain and offset have to be calibrated for every current range and every voltage range for both the force and the measure. So that's a lot of calibration factors. And right now I'm doing it the absolute brute force way. I see what the error is, offset error, I put in a correction factor in a variable and recompile the code. And then, yeah, it couldn't get any more brute force than that. Clearly, the calibration numbers should be, first of all, they should be calculated automatically, and second of all, they need to be stored in EEPROM. So that's another test that's coming. So, if you're interested in this project and you want to find some more details, I have a pretty comprehensive web page with all the information on it. And my web page is at djerickson.com. That's djerickson.com. And the page is /DIY_SMU. And you'll see all the rest of my projects there under djerickson.com, there's a link to the DIY-SMU project as well. So check it out, and hope you enjoy it. Thank you.